Welcome back. This is the second part of a three-lecture series on mathematical modeling of porous electrode. This is still at an introductory level. So in this lecture, we will look at the current or charge balance equation. Let's once again look at the electrode structure we are looking at. So this black object is indicative of a current collector. Current collector is a material that has high electronic conductivity. It can be copper or aluminum, depending upon corrosion of materials. Okay, so typically the choice of current collector is based on two properties. One is it must be a very good electronic conductor, that's for sure. And in addition to that, there are issues of corrosion that goes into the choice of the current collector. Then what we have is a three-dimensional electrode. What we mean by that is it has significant surface area in a volumetric element. So how is this surface area achieved? It is via using a very porous structure. In this case, we have shown idealized pores, but in general, the pores are randomly oriented. So inside these pores are electrolytes that fill in these pores. And because of the very high surface area possible in this three-dimensional element, the interfacial reactions, which are the electrochemical reactions in this case, are much higher. So what is our objective? We are interested eventually in the current, right? So the current is dependent upon two potentials. There is a potential that exists within the electrolyte that fills in these pores. Then there is a potential that is associated with this electronic conductor. So this three-dimensional object has two kinds of conductor, right? This is the electronic conductor, and within these pores are the electrolyte, which are electrolytic ionic conductors. Associated with these two structures are two different potentials, and we have n species. Therefore, we have concentrations associated with the n species. To get the current as a function of these parameters, we have 2 plus n unknowns. There are two unknowns here and n unknowns here. So to get these two unknowns, we need 2 plus n conservation equation. So it can either be conservation equation or some constraint equation, you would see as we go into the next lecture. Typically, what conservation equations we are looking at are either a current or a charge conservation equation. Then you might also have material balance equation, which is another form of conservation equation. The typical constraint equation we are referring to is the electroneutrality, the constraint of electroneutrality that is present here, because charge separation is a highly energy penalty phenomena. It involves a lot of energy. So typically the systems are electroneutral, even in electrochemical systems. So what is that we are trying to do? So we are trying to do some kind of an volume averaging. So when you do a volume averaging, you want to create certain homogeneous description from an inhomogeneous object. So what is the inhomogeneous object we are looking at? We are looking at an inhomogeneous object shown with idealized pores here. Why is it inhomogeneous? Because on some parts we have electrolyte, on some other parts we have electronic conductor. But when we homogenize, that is using certain volume averaging procedure, I consider a volume element that not only contains this solid electronic conductor, but also the the parts which are ionically conducting, so that I can talk about a homogeneous element across the porous electrode. So this has to be understood. My volume averages are bigger than the small pores which contain the electrolyte, or the small elements which contain the electronic conductor. So it has to be greater than either of these small features, so that I can get an homogeneous description across the porous electrode. So this is similar to averaging, which you might have seen in continuum mechanics. For example, in your first fluid mechanics class, we might have defined density. So when you try to define the density, you take an volume element which is much larger than the size of the atoms which you are looking at. But this volume element size length scale is less than the length scale wherein there is variation in these macroscopic quantities. For example, if you think about density, and let's say you are talking about density of a liquid, and there is a thermal temperature variation in the liquid. Because of the variation in temperature, then there would be density variation. So our averaging volume element should be much higher than the the volume of the atoms that goes into the liquid, but it should be smaller than the length scale wherein there is density variation. So what is the analogy here? Our length scale considered in the porous electrode for averaging is greater than the length scale of the small pores, as well as these electronic conductors, but it should be less than the length scale wherein there is a variation in the electrode current across the porous electrode. So we will look at the current distribution in subsequent lectures. So I'm just giving you an idea of how to think about this averaging, volume averaging elements. So what are the assumptions here? So first assumption we are making is that the current collector, that is this black object, is at a constant potential. Then we also assume that the current density at the current collector is uniform. So there is no variation in the current across this current collector. Why do you do this? You do this so that you effectively make the description of porous electrode as an one-dimensional problem. There can be variation along this axis in this direction, but there is no variation along a direction perpendicular to this axis. So effectively, it's one-dimensional problem. So variation along this direction is what we are going to be considering. In addition, there is another complexity which we are going to neglect for now. What is this? We introduce the porous electrode so as to have significant surface area, surface interfacial area. From fundamental electrostatics, Q is equal to C times V, right? Charge is equal to capacitance times voltage. So dQ by dt is I, is equal to C times dV by dt. So whenever you have significant interfacial area, there is also a possibility of large capacitative currents. Okay, so because the capacitance is proportional to the interfacial area. So for now, we are going to neglect the capacitative currents, but these charging or capacitative currents can be modeled and included at a later stage. So this is perhaps more straightforward introduction. We will look at how to introduce this at a later stage. For now, we are neglecting capacitative or charging currents, charging or discharging currents, because these are indeed significant in a porous electrode because of the large interfacial area. So again, there is an additional terminology which we'll be using in the next few slides. I want to clarify it here. So when we talk about actual areas, we are talking about uh, these kinds of structures, right? There is this interface between the electrolyte and the electronic conductor. These are the actual surfaces. Okay, so this is a cross-sectional view, and there are such interfacial structures within these pores. The interface between electrolyte and the electronic conductor, that is referred to as the actual area. That can be quite significant in a porous electrode. As opposed to that, the superficial or a geometric area will be much lesser. So what are we referring to that? So this is the superficial or a geometric surface area. Typically, the actual surface area is many hundred times more than the superficial or geometric areas. But these superficial areas are useful because in most of our discussion on current density and the current that is collected at the current collector, we would be talking about a current density wherein the overall current is normalized with respect to superficial or geometric surface area. So this is the superficial or geometric surface area, whereas the interfacial area that exists between the electrolyte and the electronic conductor is the actual surface area. So we will move on. So we have two boundary conditions. So one, we are going to refer to this region as x equal to 1, x equal to 0, and this is x equal to L. And as it's an effectively 1D problem, these two specifications are enough. So electrolyte fills in the pores, and then we are going to specify two current densities. So here I1 refers to current in the solid phase, which is an electronic conductor. So this current density is specified with respect to the superficial surface, which we specified in the previous slide. So at x equal to 0, that is at this cross section, the current density in the solid phase is equal to the overall current density divided by the superficial surface area. So this is true only at x equal to 0. Then we would also, in addition, this current density is associated with a particular potential phi1 that is associated with the electronic conductor. So again, to emphasize, this A is referred via the superficial or geometric surface area. Likewise, we can refer to another current density. This is the current density associated with the liquid phase, which contains the electrolyte. Again, we are referring to the current density with respect to the superficial surface area. We can, this current density again is dependent upon a potential phi2 that is present in the electrolyte. So at x equal to L, that is at this cross section, this current density is equal to overall current density divided by the superficial surface area. So why is this so? Let's understand these two constraints or these two ways of specifying the boundary condition. So at this cross section, the only current that can pass through is the electronic current, okay, because there is no further transport of the electrolyte into this cross section. Therefore, all the current at this cross section, that x equal to 0, has to be electronic current. At this point, so, this note that this structure is adjacent to the electrolytic phase. And it may also have a separator touching to this cross section. The separator might be another porous structure with just the electrolyte present without any electronic conductor. So at this cross section, you have only current due to the electrolytic phase. So at this cross section, there is current only due to ionic species. At this cross section, you have current only due to electronic reasons. So you have electronic current here, you have ionic current here, but in between x equal to 0 and x equal to L, this is the porous electrode, you will have both ionic and electronic current. So sum of these two currents has to be a constant. What does this mean? This just means that there's no charge accumulation in between these regions. So that is what this condition means. The sum of the ionic current and the electronic current happens to be a constant. This is just indicative that the charges do not disappear or appear in between these two regions, and charge neutrality is maintained. So what we need to understand is that as we go from x equal to 0, wherein there's only electronic current, to x equal to L, where there's only ionic current, how does this transition take place? And during this transition, I1 and I2 may vary, but the sum of the two currents will be a constant. Just understand what is happening here. So supposing there are some ions, okay, so let's say lithium plus is moving in the electrolytic phase in the pore, that current due to the lithium species may disappear because the lithium may combine at the interface between the electrolyte and the electronic conductor. And with this disappearance of the ionic current, there is a change in the electronic current. So this ionic current and the electronic current are well balanced. And why are they well balanced? Because of the interfacial reactions that occur between the electrolyte and the electronic conductor at these interface of the pores. Let's move on. So an important quantity in the porous electrode is this quantity, which is a measure of the combined surface area present in a unit superficial volume. So this is an important quantity that helps us to move from the interfacial surfaces to a volumetric description that is required in a porous electrode. So the combined surface area can be very high as opposed to the geometric or superficial surface area. So for this system, for example, the combined surface area is 2.5 meters squared, whereas the superficial or the geometric surface area is only 0.1 times 0.1. Okay, so this is much less compared to this surface area. And this quantity A, the combined surface area divided by superficial volume, has a unit of 1 by meter, as you can see from these dimensions. So this is a large quantity, which is indicative of high surface area present in the porous electrode. So a way to visualize this in 2 dimensions is that imagine there are circles present in a 2-dimensional surface. So if I want to increase the interface between the circle in this areas, I have to increase the number of circles that are present. So corresponding to this quantity, in a lesser dimension, I can think about the perimeter of the surface to the overall surface area that is present. If I have to increase the amount of interfaces that is present, I have to increase the number of circles that I place in this two-dimensional surface. So going into three-dimensional description, instead of imagining a circle, I can imagine spheres that are suspended in a volumetric element. So if I want to increase the interfacial area between the spheres and the electrolyte, the spheres can be the electronic conductors, and these blue regions can be the ionic conductors, the electrolytic phase. So if I want to increase the interfacial area, I have to increase the number of spheres present in the volumetric element. So what does that help me? It helps me to think about an volumetric charge generation rate. As soon as I say charge rate, I'm talking about currents. And when I say volumetric charge generation rate, I'm talking about currents present in or currents that are generated in an volumetric element. So let us understand, or how do I define the volumetric charge generation rate? I define it using two quantities. One quantity is A, which I have mentioned here. Another quantity is a quantity which you've seen in an idealized interface between the electrode and the electrolyte. So in the previous lectures on electrochemical kinetics, we talked about just the current density. In that case, you had a planar surface, and this planar surface was the interface between a planar electrode interfacing with the electrolyte. So this ion is the current density associated with the actual surface area. In a porous electrode, we have the surface area. These surface elements are randomly oriented in all directions, and which we have idealized using cylindrical pores. So this current density is with respect to the actual surface area, which is the surface area is quite large, and this current density is reference to the actual surface area. So we do know how to think about these current densities. We have represented this phenomenologically using the Butler-Warmer equation or some approximation to the Butler-Warmer equation. That can be the Tafel approximation. We do know how to think about how to express these current density with respect to actual surface area. So when we combine this quantity A times this quantity, we get to a volumetric charge generation term. Why is this important? You will see in the next slide. So what we are trying to do is a balance equation representing a charge balance. So supposing we take this quantity I2, remember this I2 is a current density given by current divided by the superficial surface area or the geometric surface area. So this quantity is the divergence of this current density. So this is the difference in current density normalized to the superficial surface area is equal to some generation term, right? So these kinds of balances you have seen many times in the past in different contexts. So how do we think about this? So this is a quantity which we elaborated in the previous slide. This is a volumetric charge generation term. So how do you think about this? You have one flux. Let's say the incoming flux is different from the outgoing flux. This is kind of balance which you typically do in typical transport phenomena classes, what is referred to as the shell balance, right? The incoming flux is different from the outgoing flux because of a generation or disappearance in the volumetric term. So there is a volumetric term that can change with respect to time. And the reason why it changes with respect to time is because there is a difference between the incoming flux and the outgoing flux. So this difference between the incoming flux and outgoing flux is indicated by this term. And this volumetric generation term is associated with this volumetric element that is shown here schematically. So there is a sign convention we adopt. A positive sign means there is an anodic current that is present, that is positive, representing the current into the electrolyte. So if this term is positive, these two terms add up to 0. Why is that so? So the current increases. So this term by itself is positive term. So there is a negative term associated with that. So this term is negative, this term is positive. The sum of these two terms happen to be 0. It is just a sign convention. So likewise, we can think about the current in the solid phase. As always, this term, this current density is normalized with respect to the superficial area A. So this term indicates difference between two fluxes. Like we had two fluxes here, we have two fluxes in the solid phase associated with the porous electrode. That difference in fluxes is due to a volumetric charge generation term that is due to the interfacial electrochemical reaction that exists between the electronic conductor and the electrolyte phase. So again, there is a charge convention. This negative sign indicates charge leaves the solid surface. So ion is negative. So this overall term is negative. So there is a charge decrease. So that will be a negative term. Combined with this negative term, that would be a positive term. So this positive term would cancel the negative term to give rise to the 0 here. So it's just a sign convention. Go through the sign convention. So this is important when once you get on to numerical computations. You can adopt a different sign convention, but you have to be consistent in the way we use this sign convention. Yeah, let's move on. So this is just a mathematical representation of a conservation law, right? The charge, when the currents change, the currents are changing because of volumetric charge generation rate term. Okay, so this is the difference in the current fluxes. That is because of the difference, that's because of a volumetric charge generation rate term. So in the next lecture, we will look at another conservation equation which arises due to material balance. That we will see in the next lecture. Thank you.